Welcome to the Explainer. So, have you ever stopped to wonder why the entire global power grid, like every massive transmission line and industrial network out there, uses three phases instead of just one? I mean, it's a completely universal design choice. Today, we're going to look at the exact physics and math behind why that is. Let's just dive right in.
To really wrap our heads around this, we got to look at the mechanical reality of power delivery. Imagine a motor running on single-phase power. Its torque pulses twice every single cycle. In the physical world, that means the power is uneven, literally shaking the shaft of the motor under a heavy load. Now, contrast that with a three-phase system. That exact same motor receives perfectly smooth, constant torque, zero pulsing. And honestly, this perfectly illustrates our foundational concept for today. Three-phase equals constant power. That single physical difference, the complete elimination of the power pulse, is the exact reason generation, transmission, and distribution all run on three phases. Think about it. When you're generating hundreds of megawatts or running massive industrial machinery, those single-phase pulsations would create shaft vibration and noise so severe it could literally destroy the machines. Constant power is the structural bedrock of the grid.
So, how do we actually create that constant power? Well, a three-phase system is made up of three sinusoidal voltages of equal magnitude. But here's the kicker. They're each shifted exactly 120 electrical degrees from the next. We call them phase A, phase B, and phase C. Because of that 120-degree shift, they peak one after the other in a very fixed rotation order. We call this fixed order the phase sequence, and it's basically the invisible heartbeat of the grid. That 120-degree shift also defines our voltages. In a balanced three-phase system, the line-to-line voltage, which is just the voltage measured between any two distinct phases, equals the square root of 3 times the phase-to-neutral voltage. This is an absolutely vital mathematical constant for electrical engineers. It's exactly where your familiar industrial voltage pairs come from. For example, if your phase-to-neutral voltage is 277 volts, multiplying that by the square root of 3 gives you a line-to-line voltage of 480 volts. And this leads to a massive economic payoff. Because three-phase power is perfectly constant, with the pulsations from each individual phase completely canceling each other out, you can deliver the exact same amount of power using significantly less copper than an equivalent single-phase system. You literally just need smaller conductors. That is the huge structural advantage that made three-phase the default for every transmission line on the planet, drastically reducing material costs across thousands and thousands of miles. Okay, let's pause for a quick field check to test our understanding. Imagine you're out commissioning a brand new three-phase motor at a job site. You power it up, but instead of driving the pump forward, the shaft is spinning backward in the completely wrong direction. So based on what we just learned about how three-phase power operates, what do you think is the most likely wiring fault that happened during installation? If you guessed a swapped wire, you hit the nail on the head. Remember our fixed rotation order? A, then B, then C. If an installer accidentally swaps any two of those three-phase conductors during termination, it completely reverses the phase sequence. The motor just follows the sequence it's given, which causes it to spin backward. Fortunately, it's a super quick 5-minute fix once you know what phase sequence actually controls. You just swap any two phases back, and the rotation instantly corrects itself. So, let's lock this in. You probably came in knowing AC power exists, but now you know exactly why the grid is three-phase. It guarantees constant power delivery, which eliminates that destructive mechanical vibration. Economically, it requires smaller conductors, drastically reducing copper costs. Functionally, its fixed phase sequence drives motor rotation. And mathematically, that 120-degree shift defines the strict line-to-line voltage relationships that power our industries. Next up, Delta-Wye and per-phase analysis. Let's see how engineers actually calculate these networks without getting totally buried in heavy calculus. Let's be real for a second. Three-phase math looks absolutely brutal until you learn one brilliant trick, the Delta-Wye transformation. This is essentially a mathematical hack. It allows us to convert complex delta loads, which are shaped like a triangle, into a much simpler, solvable equivalent circuit shaped like a Y or a star. When we have a perfectly balanced network, which, to be fair, most normal grid operations are, converting a complicated delta load into a Y load is incredibly simple. The impedance of the equivalent Y circuit is literally just the impedance of the delta circuit divided by 3. That's it. ZY equals Z delta divided by 3. But, you might be wondering, why go through the effort of transforming the circuit at all? That brings us to another really great question. Why is the specific transformation so vital? Like, why do power systems engineers almost always convert delta loads to Y loads before trying to solve a circuit instead of going the other way around? What's the strategic, time-saving reason for forcing our math toward that Y shape? Take a second to just think about the physical shape of those connections.
Well, here's the secret. The Y's neutral point is the ultimate shortcut. You see, only a Y connection possesses an accessible center neutral point. A delta connection is just a closed loop with no neutral reference, meaning you're stuck writing complex loop equations across all three phases simultaneously. But once every element in your network is converted to Y and shares that neutral point, you have the exact reference you need to completely isolate and solve just one phase all by itself. And that unlocks what we call the per-phase analysis shortcut. Here's how it works in 4 really simple steps. Step 1, use our formula to convert any delta loads to Y. Step 2, isolate just phase A and its path to the neutral point. You can completely ignore phases B and C for now. Step 3, solve that one isolated circuit using basic high school level Ohm's law. And finally, step 4, take your answers for phase A and just shift them by 120 degrees to get your answers for phases B and C.
It's pretty amazing, right? This brilliantly illustrates how an intimidating, multivariable 3-phase problem collapses into a super basic single-phase calculation. You literally throw away 2/3 of your circuit, solve one phase, and shift 120 degrees twice to get the rest for free. They have the exact same magnitude, just different angles. This is arguably the single biggest simplification in power systems engineering, and it's for sure why absolutely every textbook and computer load flow program out there utilizes this exact per-phase method.
Before we wrap up, though, I do need to note that this accessible neutral point in a Y system isn't just a convenient math trick. In the physical world, it's actually a critical protection decision. That neutral point provides a physical path to run a conductor straight into the earth. Neutral grounding means that if a fault occurs, dangerous currents have a safe path to flow to ground, rather than building up on the metal frames of the equipment and putting personnel in danger. So we've learned how to collapse basically any balanced 3-phase network into a single-phase equivalent that's super easy to solve. But there's a catch. We've only really looked at a system with one voltage level. The real power grid uses transformers to step voltages up to hundreds of thousands of volts for transmission and then back down for distribution. So how do we mathematically model a massive grid with multiple different interconnected voltage levels without our math completely falling apart? Well, that requires one more crucial trick called the per-unit system, and that is exactly what we are going to unpack in part 2. Thanks so much for joining me on this explainer, and I'll catch you next time.